What four broad-scale factors control global physical gradients on Earth? Most, if not all, broad-scale physical gradients, and we're talking about things like decreasing air and water temperatures towards the poles and so forth, are controlled by four global factors. The first of these is latitude, which I'm using here as a shorthand to address why gradients like temperature, precipitation, wind, and so forth aren't uniform as you move north or south across Earth's surface. The quick and dirty explanation here has to do with the way that the sun's rays intersect the Earth. At the equator, the sun shines directly onto the Earth. Near the poles, similar rays shine over a much wider area. This helps to explain why low latitudes, near the equator, which is 0 degrees, tend to be warmer than high latitudes, near to 9 degrees, which is at the poles. Solar energy is the major driver of difference in temperatures across latitudes, and it's really the spherical shape of the Earth that controls the amount of solar energy that reaches the surface in any location. Temperature decrease tends to correlate with an increase in latitude, but Alexander von Humboldt and many others since have noted that temperature also decreases with increasing elevation. Why is that? Air pressure at the Earth's surface is equal to the weight of all the air in the atmosphere above it. The length of the air column, which is all of the air above a particular point, decreases with increasing elevation. In other words, the higher you go, the less air is above you, and the less dense the air is. You experience this as a drop in pressure. What does that have to do with temperature? Air that moves over high elevations expands in response to the reduced pressure. Expanding air experiences adiabatic cooling, which is the loss of heat as the air's molecules move further apart. Higher elevations also lose some heat via radiation to the atmosphere, also because the air up there is less dense. It's also important to recognize the Earth's tilt of 23.5 degrees. The axis on which the Earth rotates is tilted with respect to the plane of Earth's orbit around the Sun. If the Earth's spin axis was perpendicular to the plane of Earth's orbit around the Sun, there would be no tilt. But it isn't perpendicular, and it is fixed at 23.5 degrees with respect to the plane of orbit. That tilt does not change as the Earth orbits around the Sun. The tilt is related to why we have seasons, or in other words, why our temperatures and day lengths change on pretty reliable annual cycles. The seasons happen reliably because the Earth's tilt is constant during the annual revolution around the Sun. Over the course of a year, the Earth's changing position means that parts of the surface receive less or more solar energy compared to other times in the year. During the northern summer, for example, the tilt is such that we have longer day lengths and we experience an increase in temperatures. No matter the time of year, the tropics tend to receive the most sunlight and experience the highest temperatures. We define the tropics as the latitudes between 23 degrees north, the Tropic of Cancer, and 23 degrees south, the Tropic of Capricorn. Those latitudes are not coincidental. Because of the Earth's 23.5 degree tilt, the farthest north and south the Sun appears to be overhead during the course of any year is 23.5 degrees north and 23.5 degrees south, at the summer solstice and the winter solstice, respectively. The fact that the tropics get fairly constant solar input through the year has global consequences in terms of climate. Warm air tends to rise, so air that is warmed by incoming solar radiation in the tropics rises. That air also tends to be humid. Why is that? It helps that humid air is actually lighter than drier air. That seems pretty counterintuitive that humid air would be lighter than drier air. But let's think of it in terms of molecules. Humid air will have a greater proportion of water vapor molecules, or H2O, the second molecule. Drier air will have a greater proportion of oxygen molecules, O2, or the first molecule. Which of those two molecules is heavier? If we add up their atomic weights, it turns out that it's O2, so the air with the greater balance of O2 is actually heavier than the air with the greater balance of H2O. Warmer, humid air rises around the equator. Denser air from the north and south flows towards the equator to fill the low-pressure area caused by the rising of hot, humid air. Together, these actions, which form a cycle when you look at their atmosphere and profile, form a Hadley cell. Similar atmospheric cycle cells occur at greater latitudes too. Wind has a big role to play here too, and you'll note that a map like this usually shows that the major wind patterns on Earth's surface are curved. Why is that? This has everything to do with the Earth's rotation on its axis, which is the final of the 4 big factors. I'll link you to a video on the consequences of this spin, which we call the Coriolis effect, but I'll leave you with a quick review. The 4 factors that control global physical gradients on Earth are spin, tilt, the Earth's orbit around the Sun, and the Earth's spherical shape, which causes sunlight to fall unequally on the surface.